Okay, great. So welcome everyone to this session. Andrew Perry from Springfield College is going to share with us about Euler's differential equations.
Thanks, Tova, and thanks to Simeon for making this talk and this whole excellent conference possible. So this talk is about Leonhard Euler's differential equations, and Leonhard Euler was a Swiss mathematician. He also, I believe he spent the first part of his life in Switzerland, of course, and then moved to St. Petersburg for some time, and then moved back to Switzerland. I believe it's Basel. So he spent quite a lot of time in the Russian royal court, and he is just an amazing mathematician. This is a differential equations conference, but I think if you're interested in the history of mathematics, then Leonhard Euler really steals the show in a lot of fields of mathematics, and differential equations is one of them. So I hope you are get as excited and as impressed at Leonhard Euler as I am. Euler's research areas are vast. He did work in analytic number theory, in complex analysis, infinitesimal calculus, mechanics, fluid dynamics, optics, astronomy, and music theory. And he was a mathematics researcher, but a lot of his work was also expository. He was among many, many publications. He wrote a fine work called Letters to a German Princess, where he was educating this German princess with expository work in a number of fields. A really wonderful organization, which sadly is not as active as it used to be, is the Euler Society. And I actually had the privilege of attending a talk at the Euler Society in Austin, Texas. I believe it was 2007. The Euler Society encourages scholarly contributions, examining the life, research, and influence of Leonhard Euler, explores current studies in the mathematical sciences that build upon his thought, promote translations of his writings out of their original languages, and engages in general study of the science, politics, and culture of the Enlightenment. And this is really an amazing group. For some time, this group was meeting every 2 years, and I was one of their number, but most of the folks in this organization just know incredible amounts about Leonhard Euler. A lot of people have really devoted their professional lives to studying this one individual and his contributions towards mathematics. Euler wrote a total of 866 mathematical works. And fortunately, there was this fellow named Gustav Ennerstrom, who lived from 1852 to 1923, and he was Swedish. He cataloged Euler's works and gave them numbers E1 through E866. I believe these numbers are primarily listed according to chronology. I know the works of a given year are grouped together. Most of Euler's works were in Latin and French and German. I've heard that he also has written something in English, although I was never able to find an English work, but apparently he also wrote in English and I think Russian as well. It's said that he's written some works in Russian. Quite a lot in Latin, however. There is a huge collection of works called the Oprah Omnia. There are 84 volumes planned in all. Not all of these have been published, and I believe some of them will never go into print. But in theory, there's approximately 84 volumes and 35,000 pages. 35,000 pages. So there's a list here of his works in various series. Series 1 in mathematics, 29 volumes. Series 2 in mechanics and astronomy, 31 volumes. Series 3 Physics and Miscellaneous, 12 more volumes, 9 more volumes of correspondence, and then the remaining ones are to be published online and not in print. And if you think about 35,000 pages divided by 84 volumes, these are good sized volumes as well. They're several hundred pages each for sure. So the Euler Committee of the Swiss Academy of Sciences was charged with collecting and preserving and publishing all of his scientific work. And this is an excerpt from their website. And they decided in 2005, they decided with the advent of the internet and high cost of printing to entirely stop the editions in book format. And they're creating a global edition in digital format, including scans of all the letters and original manuscripts, which their website says it was scheduled to be completed before the end of 2020. I'm not sure if that actually happened. That's actually not the only place to find Euler's works, however. You can also find them at the Euler Archive, which is easy to find by Google. And on this slide here, I've just included some screenshots here. You can search the archive by subject and index, date written, publication source, and a Strom number, or search by translated works. There's also a lot of other very interesting information about historical topics and links to a few important sites. Oops, I didn't mean to advance there. How Euler Did It is a fantastic collection of expository articles on Euler written by Professor Ed Sandifer of Western Connecticut State University. He published these articles monthly for something like 10 years or so. And actually, can you perhaps, oh yes, maybe you can see me. There's one of these volumes, How Euler Did It. If you can see this is written by Ed. It's a collection of all the columns online, but I think you can still find everything online as well. I want to show some excerpts from, I believe it's, oops, there's people in the waiting room here.
Yeah, I'm keeping an eye on the waiting room, so you don't have to worry about it.
Oh, okay, good.
Yeah.
It said 4 people entered the waiting room, but okay.
Yeah, I'm letting them in as they come.
Oh, excellent. So I've lost track of where we were. Oh, yes. So I want to show some excerpts from Euler's Institutionum Calculi Integralis, which is Latin. My Latin isn't great, so I'm showing the excerpts in translation. Ian Bruce has a lot of Euler translations online. Thanks to Mr. Bruce. So from the Euler Archive, here's a sampling of some of Euler's work in differential equations. I thought to include the entire list, but then that would have taken up 7 or 8 slides. But this is just a small sampling of his work in differential equations. Strom number 10, a new method of reducing enumerable differential equations of the 2nd degree to differential equations of the 1st degree. And you can take a moment to peruse some of the other titles. And again, there are something like 40 or 50 of them in differential equations alone. For teachers among us, Euler might be most important for Euler's method, for numerically solving differential equations. And for that, we want to turn to Institutionum Calculi Integralis Volumen Primum, or Foundations of Integral Calculus, Volume 1. And this was written in 1763, but not published until 768. For those of you who don't know the history of math, sometimes there are long gaps, long and surprising gaps. And it's in the first volume that we find his work on the Euler's method. And the PDF of this work is online, and here is the cover page. Very pretty to look at, and you can see the that it's written in Latin. This whole work is in Latin. And if you go in this volume to part 1, section 2, chapter 7, you see concerning the approximate integration of differential equations, a general method by which integrals can be found approximately. And Euler discusses some theory, but I think it's easier for us to understand some worked examples. So his paragraph 305 was to exhibit approximately the integral of x to the n dx, which I'm sure Euler knew to be x to the n plus 1 over n plus 1. So that vanishes when putting x equals 0. In other words, we would think of that as c equals 0. He's also calculating by the same method the integral of 1 over x to the n. And finally, he calculates the integral of c over c squared plus x squared. Notice c squared is cc and x squared is xx. And this is an arctangent, as it turns out that he's integrating numerically. And so here's a page from his work. And you can see that it's not organized in the same way that we would organize it today. He actually is finding an upper bound and a lower bound. And alpha is the common difference, or the step size. As alpha approaches 0, the difference between the upper bound and the lower bound approaches 0, so that he can actually be sure of finding the exact answer. So we think of Euler's method as a method of approximation, but you can also, in the limit, find the exact answer. On this slide is a nice example of Euler's method graphically to solve a first-order differential equation with the initial value. The initial value at y of t naught is y naught, and the differential equation is going to be y prime is some function of t and y. And the blue line is the original function to be approximated. A0 represents the initial value, and the red line shares the derivative of the blue line. So it moves. Let's see, can we see the mouse? Yes. Actually, I don't see. Well, no? Okay. Anyway, you can see how going from each step to the next, the red line shares the derivative of the blue line, and it goes off in a segment. You can also you calculate Euler's method using many types of software. I checked some out and decided the easiest one to use was Wolfram Alpha. You can actually type into Wolfram Alpha, you can type Euler method.
It's 5 o'clock.
Dx dt equals x times 1 over x. I just picked this equation, this differential equation, and give it the initial value, give it the interval you're interested in, and give it the step size. And then Wolfram Alpha will give you an exact differential equation result, and you can compare it to the numerical solution. And I want to add finally that Wolfram Alpha is free and powerful for all kinds of differential equations to go along with the theme of this conference and for other math. If you want to solve a linear ordinary differential equation here, it's as easy as just typing it in and hitting enter. You could certainly specify initial values. You can do a great many things in Wolfram Alpha that are way beyond the scope of this talk, but it's a wonderful teaching resource if you're not familiar with it. And that would be my final slide. So thank you all for listening.
Thank you, Andrew. Does anyone have questions? You always got to give it a minute longer on Zoom than you do in person. Here we go from the chat. What is the application of Euler differential equations?
Oh, the applications? Well, Euler's method would be a way of solving any differential equation numerically, which is wonderful if you don't want to figure out using theoretical math how to solve a differential equation. As long as it fits the right first order situation, you can get as accurate a solution as you like by using a small enough step size.
Mm-hmm.
Thanks.
I didn't notice in Wolfram Alpha, did you input the step size, or does Wolfram Alpha choose a step size?
You choose the step size.
You do. Okay, so you have control over that.
I think
cool.
Yes, you certainly can choose the step size. Wolfram Alpha will let you choose nearly anything you would want.
Mm-hmm.
Although I suspect that if you don't choose the step size, it will probably choose one for you. It's
okay.
Very user friendly.
Yeah, it's pretty smart. I didn't know it would do that though. I didn't know it would do Euler's method. That's cool. We have another question. How would you use Wolfram Alpha for systems? Can you input a system? Do you know?
Oh, yes. It does everything. It certainly will solve systems of differential equations. That's a good point. Good question.
Thanks, Abdi. Any other questions? Going once, going twice. Okay, well, thank you very much, Andrew. We appreciate the talk. That was interesting to learn about Euler.
My pleasure, and thank you to everyone.
Yeah.